important. We want to get to the shortcut rules. Can't I just use this shortcut rule? Well, I mean, yeah, but you want to understand the underlying concept too. All right. So limits is the foundation of everything. Right? Even they, like you get onto calculus 2 and calculus 3, limits keep rearing their ugly heads. So definition of a limit, I'll give you the standard, commonplace, everyday language definition, and then I'll give you the mathematical definition. All right. So limits are y values that the graph approaches. So when I say graph, I mean the curve itself approaches as x approaches a given number. All right. So that's the everyday language part of it. Now we'll sketch a graph in a second. And when I say sketch, I mean, I'm going to put it on Desmos and then copy and paste it right into the notes. But, we'll get a graph to illustrate these things, but we want to talk about notation a little bit. All right. So that's the everyday language. Now the real mathy version of it. So first off, let me identify the notation for you so it becomes a little easier. LIM stands for limit. A sideways arrow means approaches. Approaches, not approaches. Okay. L is another representative of limit. So L means limit. But it actually means it's more specific than that. It's the result of a limit calculation. All right. And then we'll have some signage, right? So I'll get to that right now. So let's say we have some constant C, right? C represents a constant. C with a little minus after it means C from the left. C with a plus after it means C from the right. Now, these are just symbols and terms. They don't mean anything yet because I haven't actually given you any rules, but this is just kind of getting you up to speed on the language that we're going to be using here, the vocabulary and all that good stuff. I wish I could get it in there, but that's not. You know what I can do? Do this. All right. So we're going to say LIM X sideways arrow C with that little minus f of x we're going to say limit or lim x sideways arrow C from the right of f of x is equal to L. All right. Otherwise, the limit does not exist. Which we abbreviate with a DNE. All right. So this is a lot of notation, but it has a reasonable interpretation, and that's what I'm going to talk about now. All right. So lim or LIM X sideways arrow C with a minus. That's read as the limit as x approaches c from the left of f of x. All right, the limit as x approaches c from the left of f of x. The second piece is the limit as x approaches c from the right of f of x. And what this is interpreted as is, if those two values are the same, we'll call that L. L for the result of the limit calculation. If they're not the same, we would say the limit does not exist. All right. So very, very strange in terms of the notation. It's almost like somebody really tried to make the notation as confusing as possible, but it's actually, once you get the hang of it, it's actually a whole lot easier than it seems. And you can see the examples below. You're given a function f of x, right? 1 over x minus 2. I'll just type that in right quick here. F of x equals 1 over x minus 2. So that's a nice, good looking rational function. What this is saying in part A is that we're going to approach, so x is going to approach a value of 2 from the left-hand side. All right, so what I'll do is I'll make a little note here of what x, x is equal to 2. All right, that happens to be the asymptote. All right, I'm going to make this a dash or dash looks nicer. I'm going to make it red and a little bit thinner. Too thin. All right. So that's x equals 2. That's the location in terms of x that a point on this graph is going to approach. So what we're going to do for the first question, all right, so for this first piece, I don't know why I didn't just use a thicker highlighter, but there we go. So for this piece, what we're going to say is that we have a point on the left-hand side of the graph, and it's working its way to the right. So from the left means to the right. You can see, hopefully, that the x value is increasing. All right, I'll do it again. Starting on the left, the x value is -7 and change, -6 and change, -5 and change, and so on. We get to around a -1, a +1. You can see that the x value is still increasing. All the limit is asking me to do is determine what y value we seem to be approaching. All right, now you may look at it and say, that y value seems to be approaching -8.772. But is it really? So what we can do is go down a little further and just follow. See, the x value is still increasing. The y value definitely is not approaching 8.772 or whatever I said before. It's even lower than that. So it's a question of, well, how low can you go? Well, it seems to be, well, it says 2 here. That's unfortunate because it's not really a 2. What's happening is your point is so close to 2 that it's indistinguishable, but it's actually not equal to 2. All right, I can actually show that to you really quickly because at this x value, or I'm sorry, the y value where it's -60, it's saying that x is equal to 2. Well, that can't possibly be the case because if I evaluate this function for an x value of 2, I get undefined. All right, so there's no way it could actually be an x value of 2 given the -60 because it's undefined. All right, you could actually go the other way and try to solve for it. Like, what would the x value have to be in order to get a result of -60? It's kind of a nifty idea. Let me just show you that real quick, because a lot of people easily lose sight of what type of techniques lend themselves to the calculator and what you should do by hand. You could solve any equation, whether it's the graphing calculator, the TI, or Desmos calculator, just by putting the left side of the equation in as one equation and the right-hand side in as another. So for example, if I want to solve, just kind of a little sidebar here, if I wanted to solve for x where y is equal to negative 60, I could cross multiply and solve, but what I can do is I could let this be equal to one equation. I would say y equals negative 60. And I would let this be equal to another equation, y equals 1 over x minus 2, and find the intersection. All right. So that's what I would do here. You know, I'll turn this one off so it doesn't get in the way. Y equals negative 60. Oops, equals. And y equals 1 over x minus 2. And see where they intersect. All right. Now, of course, it's going to be difficult, but if I zoom in like a lot, you see it's giving me something other than the 2. All right. You just got to zoom in and you'll see. But, you know, that's kind of like in a quick aside. I wanted to make sure I went over that. I'll show you how to do that on TI also. Because a lot of people don't really know that kind of skill. I always try to remind people wherever possible, and this class is not called algebra, so you don't want to get bogged down with algebra. Right? So bottom line is we're still not at the x value of 2. I can continue on. I can drag points. You know, it thinks it's gone vertical, but it really hasn't. The bottom line is this graph is infinite. All right. If you follow this curve from left to right as you get closer and closer to the x value of 2, the y value that you're getting closer and closer to would be infinity. I'm sorry, negative infinity because you're going down. All right. So you can follow the graph or you could do it by points. It's a little trickier to do by points just because, you know, you have to have the points available. But what you can do is actually, yeah, that's funny. Let me try it with this one. I must be thinking of something else. There is an option to long press on an equation and make a table out of it, but I must be misremembering that. I don't know what I'm thinking right now. I'm thinking that I'm starving. That's what I'm thinking, probably. Pizza's on the menu tonight in case anybody's wondering. So coming in from the right, same idea as you go from right to left. Right, that little notation here, that little plus sign, again, it means coming from the right, not to the right, but from the right. So from the right, I can't make it easy. The right. So I would follow my graph coming from the right and see what's happening to the y values as they get closer and closer. As I decrease my x values towards the 2, what's happening with the y? It's increasing. Just a question of in what way is it increasing? It's increasing without bound. It's going to infinity. All right. Now, in order for this limit to exist, this one right here, these two have to be the same. All right. If these two are different, then the limit does not exist. We would say DNE. All right. Would only exist if the limit as x approaches 2 from the left of 1 over x minus 2 was the same as the limit as x approaches 2 from the right of 1 over x. All right, it would only exist under those circumstances. So if they were both infinity, your limit would be infinity. If they were both 2, your limit would be 2. But because these are different from one another, this one and this one, the limit does not exist. All right. So, like I said, I'm just going to snag that graph, pop it in there. I have this idea that we would all make it through this entire course without ever having to create a graph by hand. That would be nice. You're welcome to create graphs by hand if you want to. If you're not comfortable with Desmos or any other kind of tech, maybe you're just not a tech person, that's fine. But I'd love it if we could all just for once in all my years teaching the various forms of calculus, I would not have to worry about taking off credit because somebody accidentally drew a graph incorrectly. It's so easy to do, and I don't want that to happen anymore. It's a terrible feeling. Now, you know it from the student perspective. Now, I'm just going to get rid of the side example now. It's not needed anymore. You know it from a student perspective of like, oh, you took off a point for that. I know it from the teacher perspective of like, oh my God, I have to take off a point for this and you're going to hate me for it. So creating the graph using technology, it just alleviates a lot of that stress, right, on both ends. So I'm kind of asking you to do it, but it's up to you. You see how I copied and pasted into here? I took a screenshot and I put it in like that. I don't even need that from you. When you submit, just submit the share link to your Desmos work, and that's fine. All right. So let me get a fresh new one here, a new blank graph. We have f of x equals x over x plus 3. All right, so good looking graph here. This is asking us to find the limit as x approaches 3 from the left, 3 from the right, and then just 3 in general. And by 3, of course, I mean -3 because there's a negative right there. Right, so let me draw a vertical line to represent x equals -3. I'll make it dash like it did before. I'm not going to worry about the thickness. So from the left, I'm following the curve. I want to be thinking about where the graph is going. It seems to be going up. Just a question of how far up. Well, it never stops going up. I can turn this one off, make it more obvious. All right, it's always going up. So I would say, what's the mathematical symbol to represent always going up? That would be infinity. Right? From the right, as I get closer and closer to the x value of -3, it appears to be going down. How far down? All the way down. All right, all the way down to -infinity. And because these two are not equal to one another, if they were equal, that would be our limit, but they're not equal, so we would say the limit does not exist. And it's kind of natural to get a little bit thrown by this concept of a limit, because if I were a student in the class, I'd be like, okay, so exactly how does this connect to things like speed limits? Because I don't remember a speed limit being infinity, although sometimes I drive like it is. Although my car doesn't always want to cooperate. So I want to max. I want to go to, like 200 miles an hour, and the car's like, nah, we're good at like 100. Not to say that I do that very often, but sometimes I have to admit. Well, you know what? I don't know how this works. Like if I post something on YouTube confessing to going 100 miles an hour on the highway, I can't imagine that would be a legally admissible thing, but maybe I should avoid making commentary like that, because then I get a ticket in the mail or something. I don't want that. Actually, they do more than you go 100 miles an hour. They do more than give you a ticket. So that's considered reckless driving. So yeah, I've never gone 100 miles an hour. What an absurd and evil rumor that somebody started. Anyway. If we were like physically in person in class, people would be laughing right now. It'd be great, but it's remote. And I've had this conversation, especially with my high school students throughout the year last year. I would have students that actually sent me emails after class being like, the comment that you made like 10 minutes into class was really hilarious. I just wanted to let you know that. And I'd be like, oh, thanks. And I'd be like, well, that's a weird email. I appreciate it, but like that's a weird thing to send as an email. And the explanation was, well, I would look like a dingus if I unmuted myself to go ha 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 and then muted myself. So I figured I'd just let you know separately. I was like, oh, that's cool. But you lose a lot of the spontaneity when you're remote. So it is what it is. Might be a good time to talk to you about the word of the day. So what I'm going to be doing throughout the semester, I actually forgot to introduce this early on in the course. I just whiffed. What I'll be doing, and I've done this before, and I kind of enjoy doing it, and it works, is I'm going to have a form up on Blackboard, and that form will say word of the day submissions. It'll just be well, I mean, it's a form, but it's like a Google form, that kind of form, like a survey sort of thing. And what I'll ask you to do is when I announce the word of the day during a class session, I would just ask you to complete the form, and the form is going to ask you to say what the word of the day was for that day, and also to use that word of the day in a sentence. That second part is just for fun. Like I get a kick out of what people come up with, and that'll be worth bonus credit. All right, so it's really cool because I'm talking to a lot of blank screens and names and stuff like that. There's some people that pop in visually from time to time, but I probably wouldn't if I could avoid it. But I also like to kind of get a sense of who's actually paying attention. So because I know like historically there's been a bunch of students who kind of set it and forget it. They sign on to the course, oh, here for attendance, and then at the end they're like, oh, it's class over yet? No, I meant to log off, but I stepped out and went to the bathroom. So the word of the day is a way of me kind of gauging how many people are paying attention at a random moment in class. And also the fact that I'm discussing it right now when hopefully all of you are paying attention, but maybe there's a couple people who aren't, they'll see this link to a word of the day on Blackboard and have no idea what it is. And that's also entertaining. Okay? So be on the lookout for that. It'll be up within the next day or so. But I will tell you, and just hang on to this until that survey is available. The word of the day for today is, I really didn't think about it. I'm going to say extreme. Extreme is the word of the day. So just make a note of that. Just hang on to it.
Yeah. And
then when I post that form on Blackboard, you just type in the word of the day and use it in a sentence, and you get bonus credit. All right. So just kind of keep that in the back of your mind. When it appears on Blackboard, you'll know it, and you'll be like, oh, what was that word again? I mean, it's in the video, so you'll be able to find it. But the key is knowing that it's something that you need to be looking for. All right. It's kind of fun if you spell it that way. So you can go that way. Yeah. And, the way I said it makes it sound like it would be spelled that way. So extreme, but it's just a way to kind of keep things fun and light too, see what people come up with. All right. The next problem is like infinitely more difficult. No, it's really not that bad, but it can be a source of concern because there's an element of it that can be a little tricky. All right, so you have x minus 2 over x squared minus 4. So looks like all the other graphs. The problem is this one has a point discontinuity. All right. So a point discontinuity, as we know from last class, is a hole in the graph. Right? I know I have a vertical asymptote at -2, but if you look at the question, it's saying as x approaches a +2. All right. So I'm going to draw an x equals 2 vertical line. I'm going to look for an intersection there just to see, does it actually cross? It looks like 2, 0.25. Nice solid point there. The problem is if I go to 2 here on the graph, it's undefined, and it's kind of hard to keep my pencil on this location. I'm trying to do it at least for more than half a heartbeat. You see how it goes to an open circle there? It's 2, it's undefined at 2. But this graph is perfectly well defined at 2. All right, if I follow up this one, there is a y value when x is equal to 2. And it's 0.25. All right, so it begs the question, all right, well, which one do I go with? Well, the definition of a limit is the y value that the graph is approaching as x approaches a particular number. All right. So I'd be saying, well, what y value am I approaching? Well, it appears to be approaching that 0.25. See, we get close to 0.25 before it goes undefined. From the right, it also appears to be approaching 0.25 before it goes undefined. The key ingredient here is it doesn't have to actually get there. All right. We have this point 2, 0.25. I can make that a red open circle just so it fits with the whole scheme here. It looks beautiful. It's about the location that you're aiming for. All right. So you're aiming for a destination. You don't actually have to get to that destination in order to have a limit. So the y value that this graph is approaching is 0.25 from the left, from the right, and because the limit from the left and from the right are exactly the same, that would be my limit overall. All right, so this is 0.25 or a quarter. And we're able to do that without any algebra, all right, which is kind of nice. I mean, some of us like algebra, so, like maybe it's disappointing, I don't know, but it's very doable even without using an algebraic technique. All right. And in fact, when we talk about limits that involve asymptotes, we tend to want to go with a graphical technique just for the brevity of it. All right? We don't want to spend our entire lives just cranking out algebra for the sake of it. All right. I can tell you that there will be plenty of instances in this course where we'll have to do algebra. We don't have to go looking for it. All right. It's going to find us.
Hey, Professor, just a question. So, like, if you were to do algebra,
Sure.
how would you find it?
So what you would do is you'd factor out the denominator, x minus 2x plus 2. You would note that there's a common factor top and bottom in the fraction and cancel them. So this would simplify to y equals 1 over x plus 2. But we would then have to set our common factor equal to 0. And solve. All right, that common factor that canceled out, that it canceled out because it's indeterminate. Right, so I would take x minus 2 over x minus 2, set it equal to 0 and solve. So cross multiply, you get x minus 2 equals 0, which would make x equal to a positive 2. This is the x value of the whole. So then I would evaluate the y function, the simplified y function at that particular x value. So if y equals 1 over x plus 2, I would pop in the 2, and I get 1 over 2 plus 2, which is 1/4. So that tells us that we have a hole at 2, 1/4. All right. It also tells us if we evaluate this, that we have a vertical asymptote at x equals -2 and a horizontal asymptote of y equals 0. All right. So that's consistent with the behavior of the graph. All right. But all of this stuff would be necessary if we didn't have a technological approach to work with. All right. So it's a question of, I mean, do you want to do the algebra? Sure, yeah, that's fine. But if you get bogged down with it too much for, non-calculus related issues, then you could end up in a situation where you're running short on time for other things, like questions on the test if we're being pragmatic about it, right? So the next one, y equals, or f of x equals 1 over x squared. So, you know what, I'm going to save this one because this is a good example of a point discontinuity. And I'll post this up for you. But I'm going to create a fresh new one now. So f of x is equal to 1 over x squared. All right, good looking graph. Pop this puppy right in. This time I won't make it rectangular. Square. Okay. So just following the graph from left to right, we're approaching an x value of 0. So that's just the y-axis. I mean, I can still put it in. Make it look nice. As I approach that x value of 0, the y value I appear to be closing in on, if I could close in on anything, would be positive infinity. Now that's also happening from the right-hand side. The same deal coming in from the right, we're going to positive infinity in both cases. So that would be my limit. Infinity from the left, infinity from the right, and so therefore the limit is equal to infinity. All right. The last one has it's kind of a combo platter. So I can take, f of x, set it equal to the fraction x minus 1 over x squared minus 2x minus 15. All right, I got a pretty noisy graph here, so let me get rid of that. This has happened. Now, if you look at this, you got to be careful. It doesn't follow the same format as the other questions. Now we have 3 distinct limiting constants. All right. So on our own, we have to say, or we have to find the limit as x approaches a 5 from the left of this function f of x, and see if it's equal to, so a little question mark there, see if it's equal to the limit as x approaches 5 from the right of that same function f of x, where this whole thing is our f of x. All right, because if they're equal to one another, then that's our limit. If they're not, then the limit does not exist. All right, then we have to do the same thing again. This time I'm approaching 0 from the left and from the right, and then finally approaching a -3 from the left and right. All right, so 0. And then -3. So a couple of zeros here, 0, 0, -3, -3. All right. So this is getting a little messy, so I'll get rid of this stuff here. All right. So it's really 3 separate questions, but all related to the same graph. So the relevant values are x equals 0, x equals 5 first. All right, x equals 5. Again, we want it to be dashed. And then x equals -3. All right, so those are the relevant points along the graph itself. I'm going to make this one a little thicker. I'm going to go for 3.5. Yeah, make it pop a little bit. All right. So what I'm looking for here, oops, I turned one off for some reason. Don't know. Oh, I've moved it to -10. I don't even know how that happened. Look at that. Where am I going? -3, right? So come on, lock in there. Okay, there we go. So we'll do it one at a time. So we're focusing on the x value of 5 first. All right, so that's over here. That's in this neighborhood. So from the left of that location and from the right of that location, that's what we're interested in. We don't have to worry about all this other part of the graph here, none of this stuff. It's just the points that immediately surround the limiting constant of 5 in this case. So as I approach a 5 from the left, it does appear to be going down forever. All right. So this part would be -infinity. As I approach the 5 from the right, it does appear to be going up forever. That's a disagreement, all right, a contradiction. So in this case, we would say the limit does not exist. As for 0, I'm going to bring it in a little bit, if it'll let me. Coming in from the left, coming in from the right, I'm not approaching an asymptote. I appear to be approaching a solid point. Let's see what that point is. 0.0667. All right. Whenever you see something in that format, repeated values, like 0.0667, it makes me think that it's probably 0.06 repeated, and they just rounded it to the third digit. Right. But this is a finite y value for that given x. So let me get rid of this so there's no confusion. What I can just do is evaluate the original function, f of 0. It'll give me the decimal form, but it also gives me the option to convert it over into a fraction. So I'll just do that, and we see it's 1/15. So this location here is 0,115. All right, so I have a solid point there of 0,115. I could shut all this other stuff off just so you see it. It's a solid point, but it's going to put the decimal form on the graph, but at least you have the mathematical value. Now, if you want to get a little bit more, fancy with your Desmos, what you can do instead is say, just get rid of all this and say, I want to evaluate some point A, call it A. You can even call it C if you want, just to be consistent with the limiting constant. I'll use C. C comma f of C. And then add a slider so that I can move a point along the graph and also get the values that go along with it every step of the way. All right. So you can do that way too. All right. Bottom line is, it does appear to be approaching this number, 0.06 repeated. So you could approximate it, but if it can be represented as a fraction, you have to write it that way. So in this case, 1/15. All right. The last one, we're approaching a -3 from the left and from the right. So from the left, it seems to be going down forever. From the right, it seems to be going up forever. If I want to use my my handy dandy slider, you can get an idea of it, but it does get a little tricky once you get closer to the 3. It just disappears. I'm sorry, the -3, it just disappears. So you can kind of try to manipulate the step. Instead of going by ones, maybe you'll go by like 0.001s. I mean, it's only going to do what it's going to do. In this case, it's only going to let me go to the nearest 10th, but you can at least try, you know. But if you have an idea that it's going negative infinity in one direction, positive infinity in the other, that's another disagreement. So that's another DNE. All right. So a lot of graph analysis going on here, but it's all for a purpose because, well, a couple of reasons. One, I keep saying that we don't want to get bogged down with the algebra. That's true, but we also would love, I think, to have a method by which we can check our work. Right? We don't want it to just be, all right, I think I got the right answer, so I'm going to do it by hand. I think I got the right answer, so we're good. I'm just going to roll the dice and hope everything works out. If you try doing it by hand using an analytic approach or algebraic approach, you have the calculator technique to fall back on, or vice versa. All right. So what we're going to do now, I'm going to just kind of leave the next page. I'm going to put stars on that. You know, just ask you to have a look at these problems for homework. We'll go over them next class. And again, just a reminder, when I say homework, I don't mean that I'm actually collecting it, grading it, or anything like that. It's just for you to have tried these problems before the next class. All right. But what we're going to do is move on to analytic cases, limits as x approaches, whatever, but using a more algebraic technique. All right, so let me stop this recording.